We're continuing in section 3.1 here. We're going to talk about measuring linear association, which we call correlation. So this is going to give us some numerical ways, quantitative ways, to look at how closely these two things are related. So a scatter plot, like we talked about yesterday, displays the strength, the direction, and the form of the relationship between two quantitative variables: strength, direction, and form. Linear relationships are important because a straight line is a simple pattern and it's actually quite common. Unfortunately, our eyes are not good judges of how strong a linear relationship is. Now, we looked and kind of gave some general ideas, like saying it's fairly strong or moderately strong or fairly weak, things like that. But we can actually get a firmer numerical way of describing that through what we're talking about today. So our definition of correlation, which uses the variable r, measures the strength of the linear relationship between two quantitative variables. I do want to make it very clear, we are not looking at just the strength of the relationship period, but the strength of the linear relationship. Because there are some variables that have an extremely strong relationship, but it's going to be a squared relationship or a logarithmic relationship. Correlation is not going to be high on those because what it's measuring is the strength of the specifically linear relationship. So we're only focusing on the strength of the linear relationship. R is always between -1 and +1. If it's greater than 0, that indicates we have a positive association. Positive slope is also going to coincide with that. Being less than 0 indicates a negative association. No big shock, but good to remember. If the values of R are close to 0, that means we have a very weak linear relationship. But if it's close to either -1 or +1, doesn't matter whether it's positive or negative. The point is, if it's near the tail end of that range, close to -1 or +1, then it has a stronger linear relationship. So the farther away it is from 0 in either direction, the stronger the linear relationship. Because all the sign is indicating is whether it's a positive association or a negative association. So the extreme values, r equals -1 and r equals 1, only occur in a perfect linear relationship. So really, unless we are creating the plots or the dots using a linear equation, then it's almost never going to happen when we're using real world data. Now we may find some that are very close to 1 or -1, but they're not going to be exactly -1 or 1, and that's okay. We're not expecting something to be exactly 1 or -1 for the correlation. So here's some visuals to give you an idea. Top left, that is a correlation of 0. There is no linear relationship there at all. They are just spread all out all over the place. But I'm just moving across the top. We do see it's starting to form some level of linear relationship. They're certainly closer together in that middle one on top. So the correlation there is -0.3. It's still pretty weak because it's at 0.3, and it's negative because in general the pattern is moving downward. The next one, top right, the correlation would be positive 0.5. So the points are closer together there than they are in that middle one on top, and they're moving in a positive direction, moving up as we move left to right. That makes it a positive R value. Move down to the bottom left where the correlation R equals -0.7. Again, the negative is just telling us the direction, and the 0.7 tells us it's getting closer together. 0.7 is a moderately strong linear relationship. And then you see 0.9. Again, the positive sign is just telling us the direction. And 0.9 means it's a strong linear relationship. The points are pretty close together in a linear form. And then -0.99 is an extremely strong linear relationship. It is very, very much forming a straight line very close together are the points. So that gives you just an idea visually of what our correlation looks like. Now the formula for R, frankly, is a bit complex, even for me, to be honest, but it helps us to see what correlation is. The good news is you won't really ever have to use the formula. We're just showing it here to give you an idea where it comes from. You should use your calculator, or if you're in college doing it, you might use some different stat programs to find it. But here's how to calculate it. Again, you don't have to memorize this because you won't be required to use this formula. The calculator does it for us, which is great. So suppose that we have data on variables x and y for n individuals. The values for the first individual are x1 and y1, and the values for the second individual are x2 and y2, and so on. So the means and the standard deviations for the two variables are x bar and sx for the x values, and y bar and sy for the y values. The correlation R between x and y is, you ready? That formula! Hooray! Doesn't that just look so much... Yeesh. Yeah, so that's how you would find it if you had to do it by hand. Thankfully we don't. But I'm just curious. Do you recognize this form? Does anything look similar here to something we do elsewhere? If you guys feel up for a class discussion, I'd encourage you to pause it here and see what you guys think. The thing that strikes me the most about this is it looks kind of like a z-score, where you take your value and you subtract the mean, which is what x bar and y bar represent, and you divide by the standard deviation. Like I said, there are some other things you could draw out relationships to, but that's the one that is the most obvious to me. Alright, so facts about correlation. How correlation behaves is actually more important than the details of the formula. So knowing how to use it, that's what we really need to focus on right now. So first, correlation makes no distinction between explanatory and response variables. So it does not matter if you even foolishly label one the wrong thing. It doesn't matter which one is x and which one is y as far as the correlation is concerned. So we could completely switch which one is x and y, and we would still get the exact same R. We'd get the same correlation. And it doesn't change when we change units of measurements of either one or both. So for example, if we're talking about a length in feet and we convert it to meters, that doesn't change the R. Units of measurement have no effect on the value of R. And there's no actual unit of measurement for correlation. So beware. Correlation does require that both variables be quantitative. We can't do it with variables that are not quantitative. Correlation does not describe curved relationships, no matter how strong the relationship is. I mentioned that to you earlier, but just want to make sure that part is clear. Even if we could even plug in values that are literally on y equals x squared. We could just use the equation to get the point, so it's perfect. It wouldn't be a good R, because that's not linear. Correlation is also not resistant. R is strongly affected by a few outlying observations. So outliers have a big effect. Correlation is not resistant. And correlation is not a complete summary of two variable data. It is helpful, but it should never be viewed as kind of the catch-all or the end of the story, and that's all we need to know. So I want you, for these graphs, to estimate the correlation R and interpret it in context. So I'll pause, and I want you guys to pause and get an answer, and then press play when you're ready. Okay, the correlation here, you should have a a positive number, fairly close to 1. I'd say in the 0.8, 0.9 range is probably pretty reasonable. And what we see is that there's a pretty strong linear relationship between the number of boats registered in Florida in thousands and the number of manatees killed by boats. And that as the number of boats registered in Florida increases, the number of manatees killed by boats also increases. Okay, same thing. Please hit pause, think about your answer or talk about it, then hit play when you're ready. This is certainly a weaker R. It's still positive, I'd say. We're still heading uphill mostly. My best guess would be somewhere around 0.3 or 0.4. If you're anywhere in that ballpark of maybe 0.2 to 0.5, you're probably close enough to a good guess. but we'd say there's a somewhat weak linear relationship between the number of storms that are predicted and the number of storms observed. But it does seem overall, as the number of storms predicted increases, the number of storms observed also increases. So check out this one with healing rate. Pause it. I'd say my gut goes with maybe a 0.1 on this. There's somewhat of a positive relationship, but really only because of those 4 dots in the lower left that I even think that. It's almost no correlation at all. I think maybe 0.1 I'd understand if you put 0 on this one. I'd say there's pretty much no clear relationship between the healing rate of limb 1 and limb 2. Perhaps a very slight positive relationship. As the healing rate for limb 1 increases, the healing rate for limb 2 also increases. But mostly no relationship at all. Okay, hit pause. This one's tough. I think I'd have to guess something around negative 0.3. Now we do have some outliers that seem to go away from the overall negative pattern. The kind of, if you look in the lower left, almost looks like 3 vertical ones and then 1 off to the bottom left of that right above the negative 20. Those kind of look like outliers, but I'd say there does seem to be an overall negative pattern where it's going downhill, or a negative association. And I might guess the correlation is something like negative 0.4, because they're relatively close together except for those outliers we mentioned. So I'd say it tends to be that as last year's percent return increases, this year's percent return tends to decrease, and there's a moderate linear relationship between them. Okay, that completes section 3.1. Here's your homework. Wish you well. It'll only be a few more days and I'll be back. And maybe you're looking forward to that. Maybe you're not. Who knows? But either way, I'll see you guys soon.